Hello, I'm going to review the quiz that we had in a very short video. I just want to point out the important and critical points in the question. I don't want to solve this example in detail. The question says that the non-rotating steel shaft shown in this figure, this one, is subjected to a fluctuated loading, which is bending, and that varies from plus 20 to minus 10 kilopounds time inch. And we're asked to find a couple of things here. And a couple of information are given here, and a couple of graphs and figures at the end of the question. Okay. First of all, I'm gonna point out the critical points in the question. The first thing is this line. It says that is a non-rotating shaft. So this non-rotating shaft, this information will be used when you want to find KB, which is the marine factor. Okay. So the load is fluctuated between 20 to minus 10. So the type of loading, we can have three types of loading. We can have axial loading, we can have moment, and we can have shear. We said that axial loading makes normal stress, bending moment normal stress, shear cause shear stress. So for axial loading, the moment is F over A, and F will be given to us. For example, it says that F varies from plus 20 force, plus 20 newtons to minus 10. For moment, that will be MC over I, and in this case, moment will be given to us, which will be, for example, in this case, that's from minus 10 to plus 20. And in shear case, the equation will be torque C over second polar inertia. Okay, so here in this question, we are in the second line, so we have to use this equation, the second equation. So we're going to put the maximum moment here, and we're going to find the maximum normal stress, and we're going to put the minimum moment here, and we're going to find the minimum normal stress. Okay, so the first thing that we are asked is to find the ideal hindrance strength, SE prime. Okay, so SE prime is a function of SUT, and that's a function of material. Okay, so if you want to find SE prime, we need to know the material. In this graph, there are a couple of information are given to us. The material is steel. The surface finish is cold drawn, so this one will be used for finding the first marine factor Ka. Working temperature, again, this is for marine factor. Desired reliability for marine factor. Dimensions can be used for different cases. And there are three numbers here in this stress strain diagram. The first one is 135, and this is for this point. And this point is yield, so that's sigma yield, sigma y. This point has 240 kPsi stress, and this is the ultimate strength, SUT. And finally, this point, that's a fracture, or if it was a brittle material, that was brittle. The same point, but it is called in two different ways. Okay, so these two information are important for us. So we can get SUT from the graph, we can apply that one, and we can find SE prime. So 1 point for that one. For marine factors, we have Ka, Kb, Kc, Kd, Ke, and miscellaneous factor. So here we have 6 factors, so 6 points for the second part. Ka, I'm gonna write, for example, Ka will be some coefficient like A, SUT, and the exponent B. And these two coefficients can be found from a table. And this variable here, that's SUT, It's not SE, it's not N, it's not any other thing, it's SUT. Okay, so that's for KA. For KB, the story is different, and I do suggest you to see the marine YouTube video that we had if you want to know more about that one. But the non-rotating, it depends on if the shaft is rotating or not. It depends on the type of loading and a couple of other things. Okay, and KC and the other like coefficients that, for example, for when you want to find the temperature coefficient, we need to use these 200 in a long equation and find the temperature coefficient, or we can just use a table. For desired reliability, again, we can just use a table, or we need to find Z and then find the coefficient for that one. There is one important thing here, and that is KF, that is miscellaneous factor, and this is lowercase k, and this is different from capital KF. This is in 90%, this guy is 1. This is marine factor, but this is fatigue stress concentration. I said stress concentration factor. This KF, capital KF, is a function of KT, theoretical stress concentration, and Q, nudge sensitivity. Okay, so when you want to find this KF, we need to find these two parameters, and they both can be found from a table, from two different tables, and then we need to find this KF, and we have this KF when there is something like a fillet in the question, or when there is a hole or notch or whatever. So if the specimen was very, very simple like this, we can see KF. So KF in that case is 1. So KF is for some type of stress concentration things. Okay, and that's very, very important. This KF is not the same as that one. The same thing for here is for this A and B. For example, if you want to find a strength, each one of the items that is asked here, SF, fatigue strength, that is A n to the power of B. And in this case, this A and B is different from these A and B. Here, A can be found from F times SUT, the whole to the power of 2, divided by SE, and B is minus 1 over 3 log of F times SUT divided by SE log of the whole things. Okay, and this is N, and this is not SUT, that's a number of cycles. Okay, so the endurance strength for part C, that SE, and SE is KA up to KF times SE prime. So we can find SE prime from this guy, and then we can put that one here, put all the marine factors here, and find SE. Fatigue strength fraction. Okay, this F is a function of SUT. In this case, SUT is 240, and that can be found from a table. So what we need to do, we need to go to appendix, and we need to find a proper table, which is this one. We are looking for this F, and because our SUT is somewhere here, 240. Okay, there are two different methods here in order to read F. One of them is we can just make a straight line because we don't have the graph, and we can just read this number, or we can continue that line and read the number. But in either case, whatever you are reading here will be between these two numbers. So you can't say that is 76%, and you cannot say that is 78, because this is 78%. Okay, so for example, in this case, F is something, I'm just saying that's 77%, okay. And if it was less than 70, here I make a straight line. For example, if SUT was 20, I was reading 90%. Here I cannot go like that. This is wrong. I have to go straight. Okay. So I read the F from the table, from the graph. A strength for 100 kilocycles. So this is the equation. F, I can find A based on this one. I know F, I just read that from a table. I know SUT, I found SE, and I can find these two. And N here is not 100. It is not 100, it's 100k cycles. So this is not 100. N is actually 100, 1, 2, 3, 0. So we need to put this one here into this equation. Okay. Theoretical stress concentration factor. This can be found again from table. So we need to go to a table. Okay. So our case is not this one, is not this one. It looks like that. But the type of loading that we have is not normal. So it's not this, and this is the correct one. And if I want to find the KT, this guy, I need to find R over D, and D over D. So in this case, I can read that one. I don't know what, okay, my R here is given here. R is 5, D is 4, and capital D is 4.2. So I can find D over D, 4.2 over 4, which will be 1 over 5. So we're in this line, and R over D, and that was, R was, how much was R? R was 1 over 2, D is 4, so that will be 1 over 8. Okay, so 1 over 8 is this number here, and I go up, and then I found the intersect between that and this line, and then I go to the left, and I read that. So for example, that is 1.6. That's my KT. Okay. So I read the KT from the table, from the graph. So I found KT, notch sensitivity factor, Q. Again, I need to go to another table, another graph. And that graph is this one. Okay, so the notch radius here is half, and SUT is 240, it's upper than this one, so and half is here. For example, if we continue, that's half, because this is R in inches. If R was given in millimeters, I had to use the upper axis. And for example, this is 240, so at point half, it's somewhere here, and it's close to 1, so Q is 1. Okay, so I found that one, fatigue stress concentration. That is capital KF, which is a function of Q and capital KT. So if I want to find KF, I need to apply that Q and then KT, and that will be 1.6. Okay, second moment of inertia, because I want to find the force here. So second moment of inertia for this case will be I will be P d to the power of 4. Oops. P d to the power of 4 divided by 64. And that's important that we are using this d, not the biggest one. This d has to be used for finding the second moment of inertia, this one. Maximum and minimum stresses. Okay, for finding maximum and minimum stresses, we're going to use this equation. We're going to put the maximum moment here. We're going to put the I that we just found here. And this C is the radius and is this guy from here to here. So this is C. So C is d over 2. In this case, that's just 2 because d is 4. D is given to us, d is 4, so that's just 2. So we can find, and we can put the 20 here. We found the maximum stresses and minimum one. But what we found is we can call them sigma naught. That's mc over I. Because we have some stress concentration factor here, I can say the maximum stress is Kf times MCI. The minimum is again Kf times MCI. Okay. Mid-range and alternating stresses. Okay, sigma m is sigma max plus sigma mean divided by 2, and sigma a and write it here. Sigma a is sigma max minus sigma mean absolute value divided by 2. If you don't use this Kf here, if you just say sigma is mc over I, here at this point you need to use Kf. So that's Kf times this guy and Kf times this guy. But if you use Kf here, you don't need to use Kf here. So we just use Kf once, either for these stresses, mid-range and alternating stresses, or for maximum and minimum. So we've done these two parts. Completely reversed stresses based on modified Goodman criterion. Okay, let me see if I have a picture of that one. Okay, so this is part of the book. So if you want to find the completely reversed stress, what we need to do, we need to substitute SE with completely reversed stress. These formulas are for when you want to find the safety factors. For example, if you want to find safety factors based on Soderberg criterion, we need to use this equation. We need to put sigma alternating stress and mid-range stress here, and endurance strength and yield stress here, so we can find n. But for example, if you were asked to find reversed stress based on this criteria, we have to, okay, I'm gonna rewrite that one. That's sigma a over SE plus sigma m over sy equals to 1 over n. If I was asked to find reversed stress, I need to change this one to reversed stress. Then I can solve this equation for reverse stress and find the reverse stress. Okay. And let's see what else we have here. Number of cycles to fatigue. Okay, this is, I'm going to show you the equations for this one, and safety factors. We're going to use, again, one of these equations, for example, whatever we are asked to find the safety factors. And if mid-range stress is positive, we're going to use this equation, and if mid-range stress is negative, we're going to use that one. Okay, I'm going to show you the equations for number of cycles. Okay. Okay, so here this is the fatigue strength, this equation, and we said that if we want to find A and B, we need to use these two equations. Okay, so this guy here, this is the number of cycles to failure. So when we want to find this one first, we need to find the reverse stress, and these two components, we already had them. We found them in the previous steps. There's a question here I'm going to ask you, and I'm going to let you think about that. This equation here is for completely reverse scenario. In this case, it's not a completely reverse scenario because we are not oscillating around zero. So I wonder if this equation is still valid or not. Okay, so these are the all things that you are asked to do for this question. I made an Excel file, and I'm gonna find all the information based on that. So properties, SUT in this question, SUT for this question was 240, and the unit was kpsi, yes. SY, I need to come back to this graph, and here SY is 135. So I'm going to say 135, and the unit is kpsi. Okay, so based on this one, because SUT is more than 200, so SE prime is just 100 kpsi, the equation 6.8. If you don't know how I found that one, you can go to equation 6.8. And I'm going to find hindrance strength, but first I need to know the main factors. Okay, let me continue this one. Surface finish. Surface finish here is given to us, that's called drawn, so I'm gonna change this one to that. Rotation, come back to the equation, to the question, it says non-rotating steel, so it's not rotating. That circular, yes, the type of loading is bending. Temperature, coming back here, temperature is 200 Fahrenheit. So temperature is 200, and the unit is okay Fahrenheit. Reliability is 90%. Was it 90? Yes, it was 90%. KT, we read that one from the table, 1.6. Q was 1, so KF can be found automatically based on 1 plus Q times KT minus 1. Okay, the diameter, the smaller one, was 4. So I and J and cross section can be found. Forces, you don't have any forces. Moment. Moment is varying from -10 to 20. So the maximum is 20 and the minimum is 10. And we need to be careful to use the same units here as what we had in the question, kilopounds times inch. Yes, that's kilopounds times inch. Like for example, if that one was given to us in megapascal, this one, you see the unit is changed to kilonewtons times meter. So for example, if it was given to me in newtons per meter times meter, I had to multiply by 10 to the power of -3. Okay, just said that we need to be careful about the units that we are using. So kilopounds per times inch, and fatigue strength factor, we read that one from the table, and we said that is 77%. Number of cycles, okay, here the number of cycles has to be written in this table based on kilocycles, so that was 100 kilocycles. Okay, so let's see what we get. So for finding Ka, A and B can be found from table 6.2. A will be this one and B will be this one, and these two are a function of the surface finish. Okay, And for finding the KB, the method is using 90% stress area, equivalent stress area. So we had to, because that's non-rotating, um, here we have to use equivalent radius or diameter. If it was rotating, for example, if it was rotating, you see that DE is equals to our diameter, which is 4. So we're going to use the same DE. But because in this case it is not rotating, so that is no. Here you might have this question in your mind that should I use capital D or a small d? And this is this d and this is the other one. Okay. When I use small d here, I'm getting KB is equals to 85%, 85, almost 86%. Okay. If I use capital D 4.2, again I'm going to use 85%. So you see there is no difference. The D that we're going to use here, if you doubt which one you have to use, you use the one that gives you the lower KB, which is 4.2. But because for finding J and for I here, for finding I, we must use this D, not the bigger one. So I just leave it D and it doesn't hurt a lot. Okay. Temperature. So temperature is 200 Fahrenheit. So what this line does, for example, if temperature is given in centigrade here, it's going to convert to Fahrenheit first. If it's in Kelvin, it's going to convert to Fahrenheit first, and it's going to use the information from this one to find KD. And KC is 1 because it doesn't say anything about that. And reliability factor is 0.897, and you can see these parameters can be found from equation 620, equation 627, and table 65. And miscellaneous factor, small lowercase kf, is 1 because it doesn't say anything about that. Okay, we don't have any axial force, any torsion loading, so these two are 0. Maximum and minimum stresses can be found like this, and mid-range and alternating stresses are these two guys. And because sigma m is positive, so we can use those equations when you want to find a factor of safety. So we're going to use A and B based on these two equations that I already told you, f SUT to the power of 2 over SE for A, and minus 1 over 3 log of f SUT over SE for this one. So we can find SF based on 100 kilocycle. Then we're going to come here and we're going to find a completely reverse stress for each criteria: Soderberg, Goodman, modified Goodman, Gerber, and asymmetry elliptic. So these are the sigma reversed, and the equations are from 645 to 648, and we need to modify them. We need to substitute SE with sigma reversed, and then we're going to find the number of cycles to failure based on these equations for each criteria and safety factor for each criteria. In this example, we are just asked to find one line from this graph, this table, one from this one, and one from this. And all these things are valid when mid-range stress, sigma m, is positive, which is positive in this case. It is 1.2 kpsi. It's not, we had to use this equation. Okay, thank you.